Hi everybody. Just a little warning here that this next video is going to get into a little bit of theory and schematics and electron chasing. So if you like that sort of thing, this is going to be the video for you. If you're someone that doesn't like talking a lot about those kinds of things, well, might be one to move on past. But this was really interesting. It was a lot of fun. The amplifier modules turned out beautiful. And I got an overwhelming request for solder and chat in the last video. So the next one that you're going to see after this video will be just one of those. It'll be a solder and chat. It's going to be a lot of fun. And, well, this one's going to be all theory and a lot of talking about how things work. And I'm sure I apologize in advance if I make any mistakes. I'm not perfect. This is a secondary thing. It's just a hobby for me. So if I get some of the things wrong in here, please feel free to join in and make a correction in the comments, and I'll make sure I tag it and I'll like it and all that thing so that everybody can see it. So let's get started. Welcome back, everybody. So as you can see, I have the amplifier module, this first one that we finished in the last video. I have it connected up to a whole bunch of wires, and really what this is doing is providing power to the whole amplifier so we can test it. I'd like to test this thing and make sure that it works as it is before I go through all the bother of rebuilding the other one. Now there's a couple of considerations that we have to take when trying to bench test this amplifier. And the first thing, and I'll just shove the diagram in front of the camera for a second. The first thing that we have to look at is there are two separate power supplies. One of them is a regulated supply, and it's plus and minus 68 volts. So that would be here, and that's what drives your input stage and your bias stage. And then you have an unregulated plus and minus 70 volt supply. And they're saying 61 volts under load it'll drop to, and that provides the high current power supply for this whole section over here. So really I'm using a highly regulated power supply, and we're not going to drive 150 watts through it. We just want to power it up and bring it up to idle. So what I'm going to do is I'm going to use the same power supply to power both of these, and since these are slightly different voltages, I'm going to couple them with a 47 ohm resistor, just like that. That's just gonna, and again, we just want to, this isn't, you can't adjust this in its final setup on the bench like this. All we're going to do is make sure all of the controls work and make sure that everything is working as it should before we progress with, putting everything back together and then finding that out the hard way and having to tear it all back down. So what I'm going to do is I'm going to turn all these things on, and I'm going to adjust the controls and make sure that we can adjust the offset, the DC balance, and we want to make sure, and actually I want to be able to go from a positive offset to a negative offset to prove that both sides are reacting to the driver stage. And then second of all, I want to be able to adjust the bias so we can adjust the idle current through these transistors. So that's what all this is. We're going into the inputs with positive and negative power supply voltage, and coming out of our 47 ohm and going into the power input to the front stage. It's kind of just jumpering it together. You could probably just jumper them together and it would still work. I'm just doing this as a little bit of a precaution. And then I have my voltmeter going between the emitters of a pair of the output transistors. Again, this is not going to tell us our full idle current. This is just going to show us the idle current from one transistor to the other side. But remember, these are in parallel, and these resistors are in parallel, so you have two parallel current paths. So you'll have current flowing through each of these, which would be additive. You have two current sources in parallel. So if we read from here to here, you're only going to read part of your current, idle current, not the whole thing. So again, I'm not worried about that. I just want to make sure this all works. So here it is. I have the oscilloscope set up to the output prior to the safety circuit. I don't think this is going to activate, so I'm checking it before the relay. All right, let's turn the voltage up. And again, this is showing idle current on one pair of the output transistors. And you can see it's coming up. It's a good thing. So I have about 50 millivolts, which is pretty high. So let's see if we can adjust that. Because remember, you double that because there's two sets of transistors. Let's see if I can get this silly thing on here. And let's see if this will adjust. And yes, it actually adjusts. So I'm going to drop this down to maybe about 15 millivolts for now. I just want to get it in somewhere that it's happy. Okay, and then I'm going to move to the other pair of transistors. So I'm going to go from this one to this one. And it's the same. So that's good. Now, looking at DC offset, I don't have any oscillation or anything at idle. And you can see I have a little bit of DC offset. So the scope is set with no signal. The trace would be in the middle. So what I'm going to do now is I'm going to adjust the offset, which is back here, the DC balance. I'm going to adjust that, and let's see what it does when we adjust it. I have to be kind of careful because you have to reach around things to get to this, but I think we can handle it. Oh, come on. This camera is way in my way here. It's right where I want to be. Okay. And you can see when you adjust that, it comes down. If I can stay on it here, this resistor is right in my way. Really, this isn't the right adjustment tool for it. Let's see it coming down. Okay, let's see if we can. So there would be zero offset, and now we're going negative offset. And that is exactly what I wanted to see. So let's put this right on center. So there's no offset. For all intents and purposes, I would have to say I think this amplifier is working. Now if I look at pin 4, you can see pin 4, that would be the input. And if I touch that with my finger, I don't know if there's enough gain to get any signal out of it, but let's see. Oh yeah. Okay. So I'm going to go to a little higher voltage range. I'm going to just touch my finger on pin 4. And let's turn this down a little bit. And you can see I'm getting amplification, and when I touch the input, I'm getting a signal out. So our amplifier is working. And this is a good thing. I think everything's ready on this. It's going to be perfect. So now that we know all of our replaced components and everything is working correctly, if you look at the power supply, you can see we are only drawing 50 milliamps of idle current. So very good. Everything. Of course, that's because I have this set so low right now. I have the idle current set very low. You saw us adjust that down. So all is good. Okay, now it's time to make this module look like this module. And honestly, just doing some preliminary testing on this, other than just needing to be cleaned up a little bit, I could probably take this and just put it back in the amp and it'll most likely work. I don't see any shorted components. Of course, a couple little things, we may have some drifted resistor values. I don't know because I didn't get that far into it. But for the most part, I would imagine this would work as is. This one doesn't seem to have any damage on it. The output transistors test good. I didn't go through and test all of the smaller transistors, but I'm assuming they're good. But I'm just going to go ahead and make them match one another. That way everything will be the same, everything will be the same age, and so forth, and everything will work the same. So if you're interested in that, that's probably what we're going to do on this video. Now, unlike the other channel, these transistors are still good, so they will get removed and they will be saved for future projects. If I get another amplifier in that just needs one of these replacement transistors or something, I can use it for that, and we can keep some other gear up and running. Especially if money is an issue or originality is an issue, we'll have these spares to use for that. Some people get really uptight about changing things, putting a different manufacturer of transistor or something. When you really look at the schematics and you really go through everything and you look at the specifications of the transistors, quite often it's really not as big of a deal as you might think. But there are some instances where changing a transistor to a different model a little bit, if it's not exactly the same transistor, could make some sort of a slight change in how the circuit works. But that's pretty rare, especially if you get a transistor that's the similar specs and everything. I talk about that a lot in a lot of my videos, so you probably know that by now. But what I forgot to do is I want to mark which side is the PNP and which side is the NPN, so I don't forget. And these are 2SBs, so these are the PNP side. So let me mark that. So I'm going to do is just take a paint marker with silver paint, PNP. And the NPN we'll do here. And we're good to go. Okay. Well, it doesn't look like this has ever been worked on. That's good. Now, I think what I'm going to do on this one, I left these on for the last one, and they just kept getting in the way all the time. So I think I'm just going to pop these out and place them aside. It's really easy with the desoldering station, so I'm just going to use that and pop those out, and then I'll be right back. Alright, that is much better. It can be a lot easier to work on this now that those wires are out of the way. Okay, I'm just going to start on this end and just kind of work my way down. So I'll start with the bigger components and just kind of work my way down to the little transistors and things. And then when we're all done, we'll clean the board and make it all shiny, kind of level out all the flux on it and everything, clean it, and make it look new. Okay, I'm going to start out by replacing these two driver transistors and the resistors here for the emitters of the outputs. And the original drivers were a 2SB628 and a 2SD608, and I'm going to use this complementary pair here, which is the KSA 940 and the KSC 2073. So I'm going to replace those, and for the emitter resistors, which these ones are still good on this channel, they were all 4 shot on the other channel. Actually, one of them was still reading, the other 3 were bad. but I'm going to just put the same kind in both channels. These are wire wound also. They're 0.5 ohm. They're 1%. I think these ones might be 5%. Doesn't matter. And they're 5 watt, just like these are. But these ones are just coated, and they're pretty durable. And I am also going to raise them up off the board a little bit so that if they get hot, they're not going to scorch the board. I don't mind if they burn up and open, but I just don't want them to scorch the board and ruin it if anything should ever go wrong in the future. Now for these, let me back this up a little bit. For these resistors, what I'm going to do is I'll just put a little bend on them like this. And then what I'm going to do is I'm going to use some of this Teflon tubing. This Teflon tubing is really good because it can take a lot of heat without damaging it. The difference between plastic tubing, Teflon tubing, is the heat resistance. I'll show you here. So you can take your soldering iron and you can put it right on it, and you can see it does not melt. See, it just kind of slides on it. And, you know, conversely, if you try that on a piece of plastic coated wire, let's see if I have a little piece here somewhere. Here's a chunk of wire. You can see it melts right through it, and you get smoke and all kinds of things. So that's the difference. So it's heat resistant, and it just, after it falls off, and it will help prop these up off the board just a little bit, so if they do get hot, they won't put that charring on the board that drives me crazy. I mean, even when they work properly, sometimes these emitter resistors, if you're putting especially like a 4 ohm load and high power, they'll get pretty warm, and sometimes they can discolor the board. So, okay, the next thing I'm going to replace are these 2 resistors right here and here, and those are these 4.7 ohm resistors going from the emitter of the driver to the base of the outputs. And those original ones that were in there were little, well, I'll show them to you. These are little carbon film resistors, and I'm going to replace them. I think these are carbon film, and I'm going to replace these with flame-proof metal film, and hopefully they'll hold up pretty well. Now the next thing we're going to replace here are these 4 resistors right here. 1, 2, 3, 4. And they are all 100 ohms. You can see. And what they are for is they're located here and here on the schematic. And they're also located here and here. Okay, next thing we're going to replace is this 10 ohm resistor right here. And that is part of the, well, I'll show it to you. It's right here on the schematic. You can see it goes from the speaker terminal. See, this is right here, across here. And this is a Zabel network, I think, or has some other name, I don't know. It's the thingy that keeps high frequency oscillations off of here. And there's a 10 nanofarad ceramic cap in series with the 10 ohm 2 watt resistor, and it's directly on the output. See that? Okay, because I'm in the area here, I'm going to replace this pot right here. This is the bias adjustment, and I'm going to take this out and replace it. It is a 470 ohm potentiometer, I think. And I'm going to replace it with a 500 ohm 10 turn. And no, it doesn't matter. That extra 30 ohms isn't really going to change anything. If anything, it gives you a little more latitude for adjustment. You can see the new pot. And in case you're wondering what it is a Bourne's. And it is a, what's 3266P is in Paul -1-501LF. That 3266, the letter P, is the indicator on there that tells you that the adjustment is on the side. With, you know, it, in other words, whatever letter that is, it could mean that this adjustment would be on this side, or that it would be up on the top, or that the pins would be coming out the bottom with this coming out of this end. So that's the configuration. So you want a type P, as in Paul, to make sure that this is coming out the front and the pins are coming out the bottom like that. Other ones will work, but the problem is you'll have to bend the pins around funny to try to get them to fit. This one kind of drops in. Even though the spacing is ever so slightly different, it will fit on there. Another interesting piece of trivia here is, if you ever look these pots up, especially some of the modern ones, the single turn, let's see if I have one here I can show you in another package here. See these, you can put these in, they're a single turn, and they kind of are a drop-in replacement for these. But if you look up the specs on these styles of potentiometers, the number of actions before they're considered worn out is only 200. That means if you rotate that pot back and forth 200 times, you've just moved it past its life expectancy. So a lot of times I see people will take these pots and they'll go back and forth 100 times, you know, trying to clean them, you know, and they spray them with spray cleaner and stuff. And actually you're actually wearing the pot out more. And if you don't believe that, go online and look the part numbers up for some of those pots. Even Bournes and big names like that, you look them up. And actually, I didn't really pay attention to that. I was one of those people that did that myself until I was watching one of Alan's videos on the W2AEW channel. He brought that to our attention. I think it was something that he kind of discovered too, and was a bit surprised by. And he shared that with us, and I looked it up, and sure enough, he's right. So just keep that in mind. These are really designed to be, you know, you adjust it and you kind of leave it, and unless something fails, you never really have to touch it again. It'll just stay how it's supposed to. So here we go. We have this in, and this, sometimes it's a little tricky because you can't always bend these pins over to get them to stay in. So sometimes you kind of have to get creative with the solder. And I'll do something like this. I'll get one of the pins and I'll do something like so. And that'll get it held in place. And then we can go ahead and finish it up. It kind of holds everything steady. You kind of have to come up with little tricks for some of these things because it's not always that easy to hold everything. You don't have enough hands. So there you go, and there's the trimmer in there. But yeah, that 200 actions thing is kind of surprising, but of course these probably were not rotated, and this could probably be cleaned and reused. It's probably still good. But these single turn pots are notoriously touchy to adjust. You just barely touch them and your bias just jumps all over the place. And that's just the way they are. Even a brand new one will be like that because they're just a one-turn pot. And you need to be able to move it a little more precisely than that. Okay, the next thing we're going to replace is these 4 resistors here. And pretty interesting, if you look on the schematic and if you look in the parts breakdown, they show R27 and R28 as being 200 ohms. You could see that. And you can see R29 and R30 as being 330 ohms, which is good. But when you take these out, so this first one, you can see it is not 200 ohms, but 220 ohms, because that's a standard value. And you'll see this quite often. That's not incorrect. You can use the 220 in this case in place of a 200 and it'll work just fine. So that's what I'm going to put in there, is a 200 ohm resistor. And for this one, it's going to be a 330, which is orange, orange, brown. And I'm going to replace that as well. So we'll get those in, and then the same thing on this side, and we'll have those replaced. Okay, next thing we're going to replace is these 4 resistors here, and they're 100 ohm and 220 ohms, and they are used right in here, 33, 34, 35, and 36. And you can see how these are, once again, this is the resistor that goes from the base to the center point here where the speaker terminals would be, and this is the emitter resistor, and this will set up this driver transistor right here. Okay, next we're going to replace our 31 and 32, which is this one here and this one here. They're 27 ohms, and you can see they're right in line with the current limiter circuit, and they're in parallel with these thermistors right here. So these will actually thermally track, and TH1 and TH2 are connected right here and right here. Now I don't necessarily need resistors this big, but these are the only ones I have, and I'm not going to make another special order just to get these. So these are what it'll be, and they'll work just fine. Okay, next we are going to replace these diodes right here. There's 4 of them. And what they do, I'll show you. And for those, we're just going to use a plain 1N4007. You can also use a 4005 or 4006. They'll both work just as well. Down here, you have these diodes, and they kind of work in conjunction with these, what we call varistors. You can see they're saying plus and minus 3.6 volts there. And what the purpose of this is to prevent your VAS stage, which we'll get into this later, from overdriving. It limits the amount of voltage you can drive into the outputs. So first level of defense you have for this is to prevent this stage from overdriving the output stage and the driver stage. Now, we also have these 2 circuits here. So if you look here, you have these 2 transistors, and one of them covers the positive half cycles, and this one is the negative half cycles. And they're taking a sampling off of the actual output going to the speakers. And that's what this little divider network does here, is it determines how much current, it creates a representative voltage that tells this circuit how much current is flowing through the speaker load. If you exceed 180 watts, which would be like the total amount of voltage and current combined, then what's going to happen is at 180 watts, this transistor is going to turn on, and it's going to start to clamp down the input to the output section so that it won't let it drive any further beyond that. So technically that should protect not only your speaker load, but also your output transistors, your drivers, and all that. As you can see, it still can fail and has failed, but that's in theory what that's supposed to do. And these transistors are the associated current sources. So there's 3 current sources in this thing. Well, actually 4, but there's 3 active ones. There's this one here, it's a constant current source, this one here, and then this one up here, which provides the current source for your Class A driver section and your bias spreader here and everything. And those are all controlled by an external regulated power supply. They don't use the big power supply from over here. So you have 2 power supplies for this amp. We'll get into this later. So anyway, what we're going to do is we're going to replace these and then readjust this, and there's going to be a procedure for that. And you can see you have this thermistor there, and these will change both with temperature and with current. So as as more current passes through this thermistor, it will heat up, and then it will change its value. And I believe these ones are negative temperature coefficient, so they're actually going to clamp down this 27 ohm resistor as excessive current flows through there for any length of time. So it's kind of a variable circuit. And then right here, this pot adjusts the point at which this transistor will trip and start to clamp down the input. You can see this transistor goes straight through here, and it can actually shut down this input. And that's the whole purpose of it. And then the same thing for the negative half cycles down here. So you have, like I said, you have the power limiter, and then you have the voltage, the overdrive limiter between these diodes and this. That's why there's two diodes here. It needs those two diode drops, which is going to be about 1.2 volts or so, in conjunction with these diodes here. And these will thermally track, because they're on the heat sinks with the transistors. So they're going to actually thermally track with the amplifier, with the outputs as they heat up. And that also will affect the bias as well. So everything kind of works together. Now on this section here, we have the current source for your voltage amplification stage, or your Class A stage as they call it. This is also a Class A amplifier. They call this a differential pair, almost like you would think of an op-amp, but it's not used in the same manner, because you can see it's only picking off this one signal right here. The whole purpose of this is to provide the negative feedback. If you weren't going to have any negative feedback circuit in this, you could eliminate that and just put a single transistor here. So that's how this circuit works. So this is a current mirror, and it's different than a current source. Remember I said back here there's actually 4 current sources, 1, 2, 3. Here's your 4th, and it's not an active one, it's a passive one. It's this big resistor. It's 47K, and they're putting 68 volts. Whenever you're going to have like a tail resistor, this is called a long tail pair, in order to make it stable, you have to have, usually they'll have a high resistance and a high voltage at the tail. And if you didn't do that, if you have any amount of current flowing through this resistor, any big changes in current, it actually could still allow this to change current, and you would get what's called common mode current. So you would get a common mode signal distortion. So the common mode rejection ratio is reduced greatly by having this designed like this. Now an even better solution would be to put another current source up here, and that current source would even further reduce any common mode noise. But again, the common mode signal in this is going to be so tiny because of the big resistor and the high voltage. And you see this in other amplifier designs. Now, any other anomaly you may have in this is handled by this current mirror. A current mirror just ensures that both of these legs will always be the same current. So if more current flows on this side, it'll offset to this side and they'll balance out. And that's why it's called a current mirror, because it mirrors the current between the two sides. And what that's going to do is that's going to kind of compensate. Like I said, when you match these transistors, you usually, in this type of circuit, you want to match the VBE very closely on them, because that'll have the greatest influence, greater influence than gain, unless the gain, the beta, is huge difference. Gain does affect it a little bit, but not as much as VBE. But this current mirror is actually going to compensate for that a little bit too. So this is going to be a very stable circuit. Why it's designed like that. That's why so many of them use that. And like I said, other amplifier designs will have the current mirror on the collectors, and they will also have an active current source up here instead of this resistive passive one, with a transistor or 2 transistors, or a transistor and a diode or LED or something. So anyway, that's what's going on here. Now, a couple quick notes. First of all, this is a Class A single-ended circuit right here. So how on earth do we get, push-pull? Well, this circuit here is called a SEP, or single-ended push-pull. So what happens is this signal on this transistor will actually control this whole circuit here through your bias spreader, of course. But between the bias spreader and the way these 2 transistors are, you can see they're complementary. When you set this to Class A, meaning it's like in the middle of its operating point, then as you drive this up and down, it turns this whole thing up and down with respect to the center point. And that's kind of what gives you your phase inversion and your drive signal. And by the time it comes out through here, it's a Class AB push-pull. So probably could have described that a lot better, but you get the idea. Or maybe you don't. I don't know. Now, looking at these transistors, I wrote in with pencil what I used to replace them all with. So, for instance, I did not replace this. I think I made a couple notes of that, a couple comments to that, and we'll talk about that later. But if you were doing a restoration for somebody, I would recommend replace this transistor, this 2SA798. They get noisy. They get that static and shot noise in them. If you're not, random, some of them do, some of them don't. So precautionary if you want to replace it. This is my unit, so I can pop in a pair of transistors very easily. If it fails, I'm going to test it. For the current mirror, I'm just using a set of KSC 1845s. These are just standard small signal transistors, and the 1845s will work fine, and they're readily available. All these transistors are still available, Mauser, DigiKey, Newark, yada yada yada, all those places. For this current source up here, I'm using a KSA 1381 in place of this 2SA 858, and those are more than adequate. Actually, they are more robust than the 2SA 858. They're a lot more robust. And the same thing for this voltage amplification stage, or this Class A stage. I'm using a KSC 3503. Again, these are never going to fail because they have similar characteristics as far as gain and all that is concerned, but they can handle, they're in a larger package, so they can handle more wattage dissipation is the main thing. So you can, they'll take a little more punishment, so they should be more stable. And being in a larger package, they can dissipate heat better, so you should have a little bit better thermal characteristics with these as well. Coming over to this, these current source and your power limiter circuit, you can see they use a complementary pair of 2SC945 and 2SA733. And they do make a KSC945 and a KSA733. But there's one problem with that. The KSC945 is very similar to a 2SC945. However, a 2SA733 is not completely the same as a KSA733. For some reason, the KSA733 has a lot lower maximum current and power dissipation than these. I think an original 2SA733, like what's in here, is good for, I'm just going off the top of my head, I don't remember, but it's like 400 milliamps or 300 milliamps, something like that. And the KSA733 is only good for like 200 and some milliamps. It's substantially less. Now, in this circuit, would it work? Probably, but I don't like to put anything that has a lower rating than what I'm replacing. So a better complementary pair to this would be the KSA 1013 and the KSC 2383. They're a bigger transit. They're same kind of package but taller. So they're a tall TO92, I think they call them, and they can handle even more current than these ones do, and everything else will be very similar. Again, we just want this to last, to be robust. So that's kind of where we are with all of this. And I'm going to get these things replaced. Okay, the next thing we're going to replace is our 20, 21, 23, and 24. That's these four right here. And what do? So our 20 and 21 are in our bias circuit. You can see right there in the bias spreader. They're pretty important. So we want those to be as accurate as possible. We don't want them to drift, with a temperature coefficient or anything like that. So we're going to put some really good metal oxide 33 ohm resistors in there for that. And then 23 and 24. Now, if you want to go and order these things on Mauser or DigiKey, you don't have to order these exact ones. I'm using these because this is what I have in stock, and kind of saving me having to order them. But any good quality metal film or metal oxide resistor will work just fine in here. Oh, and by the way, just to annoy some of you, I do not point the colors of the bands in the same direction. I know some people get absolutely crazy when you do that, because they like to be able to read them all in the same direction. So I don't know. I do that just to be annoying. Hope you all like it. Of course, the electrons might just get confused which direction to go when they see all the color bands going in different directions. But, well, I guess they'll just have to learn. Okay, next I'm going to replace Q6 and 7, 13 and 14. So here's 6 and 7, here's 13 and 14. Okay, the next transistor that I'm going to replace is this one right over here. And this is Q12. You can see on the schematic it's kind of down here in the corner. And it is being fed by your overload circuit. So not only does the overload circuit clamp down the outputs, but it also, if the overload gets too high, it will turn this transistor on. When this transistor turns on, you can see the collector of this transistor goes off the board. And looking at the big picture here, it comes off the board here on pin 1, and you can see it ties into the other module. They tie together in parallel, and they go up here and onto the metering up assembly, and this is actually your speaker protect circuit right here. And D3, this little diode here, when you start drawing current through D3, it activates this circuit, and this circuit goes down, and take a look, it branches off here and here, and it actually goes to the coil of the relay. So the whole purpose of this, and that light is annoying this thing, the whole purpose of this transistor down here is to activate the speaker protect relay. So if you get a severe overload, like the speaker shorts out, like there's a short on the load on the amplifier, it'll hard shut down the speaker terminals by tripping the relay. And it is a 2SC 869, and I am going to replace it because it's a little bit beefier than like a 2SC 945. So I'm going to replace it also with a 2SC 2383. That'll work just fine. Now, something else you're going to have to be aware of. Take note of how this transistor is facing in here. See how the flat side, or the front of the transistor, is pointing this way? And that's because the pin out on this transistor is base collector emitter, BCE. But on the KSC2383, it's backwards. It's actually emitter collector base. So in order to have this pinout be correct, we have to flip it around the other way and face it this way. And this is kind of a rookie error. It's easy to forget to check the pinout of your components when you're using a replacement component. So in this instance, we just had to flip it around. Now, if we would have put that in backwards, of course, our speaker protect circuit would have malfunctioned. So be aware. Now, the next thing I'm going to address is these two transistors here. These are extremely important. Well, I say that about every component on this board, don't I? What I'm going to use in these is for the 2SA858, I'm going to use a KSA1381. And for the 2SC1439, I'm going to use a KSC3503. So these are a complementary pair. They have a lot higher wattage rating than these, but all the other characteristics are very similar, so it will work very well in the bias circuit. And the nice thing is these have a very low probability of failing, going noisy, anything like that. And we really want this to be stable, because if your bias drifts all over the place, that'll make the amplifier run hot, or could cause it to overload, or any number of things. So you want your bias circuit to always be as stable as possible. And you can see they even run this off of a separate power supply. So you can see B plus and B minus, and they're coming off the board here, and there's plus B and minus B. So these are the big power capacitors, you know, the big power supplies here for the high current. But these are actually a regulated power supply. So it's very stable, because you want your input amplifier and your bias circuit to be very, very stable. So I'm going to replace those as discussed, and I'll be right back. Okay, the last transistors we're going to address here is the current mirror for the long tail pair, which is down here. And we're just going to replace those with a couple of KSC 1845s. And they probably are good. Well, they are good on this one. And but I'm just going to replace them for good measure. And again, of all the transistors on here that you should preemptively change, it would be this 2SA798. If you were doing this for a customer or something, like you were doing a restoration for someone, you would want to replace this with a pair of, like I said, a pair of matched KSA 733s, and you would want them to be VBE matched, and even possibly beta matched if you could, but more importantly, you want them to be VBE matched for this particular circuit. And like I said, I'm going to leave these because you can see how they're in there, and when they do work, they work really well. But they do fail. They get noisy. You'll get kind of static and hiss and so forth. And if I hear that in these, again, it's very easy to just loosen the 4 screws on the board, tip it forward just a little bit, you know, like this, take them out and put the new one in. So that's not a problem at all. But again, just so you're aware of that. Okay, what to do with this relay? What I'm going to use is just a good old-fashioned Omron MY2-02 48 VDC. Hopefully you can see it there. And as you can see, it is bigger. And they did wire this up for a parallel set of relays, but that's never used in these. That's not the way it goes. Now, there's a problem here. First of all, this one has normally open and normally closed contacts. This one only has normally open contacts. So you have these 2 pins you don't have on this one. There's only Well, let me see if I have the old one here out of the other channel. It's laying around here someplace. Let me find it right here. You can see how this only has 3 pins versus 4 pins. And you can see that the spacing is different because, I don't know if you can see how they're lined up, the spacing is going to be different. So what that means is we have to clip off these 2 pins, and that's pretty easy. I'll do it right here on camera. 1, 2, all done. And now we have to make sure that these line up. And that's where you're going to run into the issues here. Okay, I found the easiest way. You can use a drill. You can use these milling bits that you can buy on eBay and Amazon and all that, but they snap very easily, and you do get a little bit of side action with them. But if you have a rotary tool, you can get these little stainless steel milling cutters, these little, here's a set right here. They're carbide, and you can, some of them are carbide, some of them are high-speed steel. And you see how tiny and pointy they are. And you can poke through there and kind of drill it out and lengthen the hole and get it how you want it. And you can see that doesn't do a bad job. Now what we're going to do is we're going to coat this whole thing with solder. Let me clean up here first so I have a little room to work. Then after you get the holes milled out properly, you can use a rotary wire brush and just take off the green mask off of there. And now we can go ahead and solder these. Now a couple of them we're going to have to put a little bit of help on there. Obviously this one's not going to touch here, and we'll get to that in a minute. But let's do these back ones first because they're properly seated. I'll try not to get too much of this flux smoke on the camera lens. Just like that. Let me move this camera because it's getting pretty. There we go. How's that? Now it's out of the way. See that? I just want to get it to flow neatly on there. And then these ones we're going to give a little bit of help with some wire. And I'm just going to do that by folding this, crimping it onto here. And the nice thing is this trace is not used on this one. This would be if you had the 2 relays on here, which we don't. So we can just ignore that. I want to get a good mechanical connection here. And then I'm going to first tack that on. You don't want it to look too janky either when you're done. You want it to be neat. That'll just hold it for the moment. And then I'm going to have this be on there, like so. I don't like things looking like bodge jobs, even when they are a bodge job. But this is really the only way to get a modern relay. It's hard to find one in that case style that will be a drop-in replacement and that will have suitable specs. So this is the next best thing you can do. And there you go. And I just want to make sure everything's covered. and I want it to look neat. And there we go. Now, just to make double sure, we will take a cotton bud. We'll go in here. I don't know if I have that green solder mask paint or not. I think I have some, but I think it's in a spray can, not in a brush. But I will put something over this anyway, just to cover it. But you can see, looks pretty nice. And there the top side, what it looks like. Okay, I went ahead and replaced the two capacitors, and those are right here and here on the schematic. And what they do is, you can see that regulated power supply coming in just adds a little bit extra filtration right on the board. That's what those are for. So replace those. And I don't know if it matters, but these are made by a company called Worth out of Germany, and they're very good capacitors. 105 and all that degree. So last but not least, we're going to tackle, you can see how absolutely cruddy these are, these pins. They're silver plated pins and they get tarnished. And what better to get rid of tarnish from silver than Tarnex. You can use Tarnex, you can use, I think Brasso sometimes works. This is one of the better ones. And you just need a tiny little amount. And I just pour it into one of these little disposable plastic cups, like that. And then I take another cotton swab. And I also have a rinse bath with water that I'll use to rinse it back off when I'm done, because this is kind of acidic. You don't want to leave it on there. And actually, before I do this, I am going to put gloves on, because this stuff doesn't like your fingers. Or should I say, your fingers don't like this stuff. So I'm going to do that. I'm going to remove my watch and just kind of take a couple little precautions here. And I'm going to just go ahead and I'm just going to scrub this down. I'm going to do several coats with it. I'm going to make sure I get the whole thing coated very well with it. And I will keep applying this stuff here and scrubbing it until they're completely cleaned off. And you can see it's already starting to come off. You want to be in a place that has some air movement in it, because this stuff stinks. There's no doubt. So I'm just going to go through and do this. When I'm done, I'll wipe it off with a clean cotton bud, and then I'll use the water to rinse it off, and I'll dry it one last time. And when these are all done, I'll be back. Okay, and when it's all done, they're very shiny. That stuff works miracles. I mean, I've tried the pencil eraser, I've tried the scratch brush, I've tried, all the different things, but the Tarnex thing, I like it. I mean, it stinks, but it works. Okay, two last components, and we'll be ready to clean the board. I almost forgot about them. One is for the DC offset, which is this pot back here. And the other one is this little electrolytic. It's actually a 220 nanofarad electrolytic capacitor. Kind of a strange choice. And you can see it's right here. And I'm sure there's a reason they use that, probably because of size. But in this particular instance, what its purpose is, it's on the base of Q12. And again, Q12 is the transistor that will trigger the protect circuit. So I'm sure this is in there to slow that down a little bit, to prevent noise from causing the relay to trip prematurely. Now, when you use an electrolytic, electrolytics typically have a much higher ESR than a film capacitor. So I'm sure that might be one reason why they did that. But of course they didn't have these multi-layer film caps back then like they do now, and capacitors can tend to, you know, the old Mylar film ones can tend to be pretty big. So I'm not sure. I'm going to try this, and if we have any problem with our circuit, you know, with the thing false tripping or not tripping when it should or something, we'll look at that a little more closely. But I don't always just willy-nilly replace an electrolytic capacitor with a film cap, because there are consequences sometimes to that. Not necessarily always, but sometimes. And when you're all done with this thing, you end up with a big mess like this, with flux and all this crap all over the board. So we're going to have to clean it off. Now what I use is just isopropyl alcohol. I put it in a little squirt bottle, and I try to level the board a little bit if I can. Let's see what we can do here. Just something to hold it up a little bit. Like that. And then I just flood it with this stuff. Like so. And that softens up all of the flux and everything on the board. And then I just take a brush that I've cut down to make it a little bit stiffer. And you want to wear gloves because the flux that's on these boards is sticky and it smells bad. It mixes with the alcohol and kind of gets in your skin and you can't get it out. So this is definitely another job where you want to wear gloves. I always do the back of the board first because invariably some of this will leak through to the front of the board and kind of make, you know, put stains on the front. So when you clean the front of the board, you'll do that last, and you can get all that stuff off of there. And the cool thing is when you do this, it kind of reconstitutes the flux on here a little bit. It takes most of it off, but it'll leave just a thin amount. And as it dries, it'll just leave this real nice shiny coat, and it'll kind of protect the board too. So looks pretty good. And you can see how shiny it is. And now when that dries, we'll come back and we'll see what it looks like. Alright, the board is all done and we're ready to put it back together. And a couple last notes here. First, what I did was I removed this ceramic cap right here. That's on here. It's a Miller capacitor, because it was directly in the way of this adjustment and it would have made it really hard to reach down in there. And I just relocated it onto the back of the board, and that just makes it easier to get in there for the adjustments. All the other ones are pretty accessible. Just this one here was impeded by that cap. So now I'm going to go ahead and mount this up, and I'm going to use, for the new transistors for the outputs, I'm going to use the MJ21194s and 21193s, and these are really heavy duty, good. These will work great for this. And I'm going to use these types of sill pads. They're not regular sill pads. They're actually pretty high end. They are adhesive backed. So what I'm going to do is I'll peel this off like so. And I'll place this back here like this. And then when I put this down onto the heatsink, it'll stick this back part to the heatsink. So when if I ever remove a transistor, the pad will stay behind, and there's no need for any kind of compound or anything. And these actually make better thermal contact to the aluminum and to the heatsink than grease and mica and all that stuff. It's actually got a much better thermal transfer coefficient. So let's get those mounted up and I'll be right back. All right, our second amplifier is done. And it'll get the same power test that the other one did. And as long as it passed the tests, we'll be ready to move on. All right, we're all connected up. And actually, I connected the signal generator this time just for giggles and grins. And I have the same setup as the first amp. And there is our output. Look at that. Beautiful. I think we have two good amp modules. So what I'm going to do is I'm going to end this part right here. And in the next video, we're just going to do a little solder and chat, because I overwhelmingly got so many requests for it. And this was kind of like that, but really we did a lot of theory in this. Didn't have a whole lot of fun, but I think it was real beneficial for all of us, myself included, to go through all the circuits and how they work and everything. And so the next video will be a little bit lighter. We're just going to work on the meter circuit board, and part of the protect circuit and everything will be on this as well, and some of the power supply as well. So this should be a fun board to restore, and just do a little bit of a solder and chat. So as always, I wish you all peace, joy, happiness, and good health in your lives. I hope all is well with all of you out there, and we'll be back real soon. And man, I can't wait to get this thing fired up to try it out and kind of find out how it performs. All right, till next time, take care, everybody. Stay well. Bye-bye.